Hello, everyone, and welcome back. My name is Mr. Cobalt, and in this video, I'm going to show you how to solve a problem that has decay rates in it. You may come across some of these problems where they, instead of giving you amounts, they give you a change in decay rates. And I'm going to show you an easy way to solve this problem. So let's get into this. So here we have a human skull, an ancient human skull, and it is measured to have a C14 decay rate of 4.50 disintegrations per minute per gram of carbon. If the living organism, living organisms right now have a decay rate of 15.3 disintegrations per minute per gram, how old, excuse me, sorry about that. So the question is, how old is the skull if you have these two different decay rates going on? The decay rate of the skull right now versus the decay rate of living organisms right now. So let's figure this out. So previously, you might be tempted, you could use this equation to figure out the K, but how would you use decay rates? Because here the N, T, and the N naught is talking about amounts, and we're not given amounts. Well, if we use decay rates, we can see the decay rate as being, this is going to be a first order decay rate. And so if you remember, you can write that as a rate law. So the rate at t, right? T is the time at which we right now have the skull, right? How old is the skull? The age is the amount of time that has transpired from the time that the human died to the time that we are at now that we discovered the skull. So we'll call that the rate of decay right now at time t is equal to the original amount, right, n naught multiplied by k. So that would be our one of our rate laws. So that would be one, or we could switch those around. So usually the constant k comes first, and that's going to be multiplied by the initial amount that we started with. Okay, and so, or that's going to be the, not the initial amount we started with, that's going to be uh, the the amount we have at time t. And then we have this other rate, right? So the rate initially, so rate naught is equal to k times the initial amount that we have been given. So now that we have these rates, the rate law is written here. Uh, you can see that the rate at time t is dependent upon how much we have at time t, and the rate at time naught is, or the initial rate is equal to, or is related to how much we had initially. Um, but notice what happens when we divide these equations. If we divide the rate laws, then the k value cancels out. It's the same k value since we're dealing with the same substance that is decaying, right? Same half-life, stuff like that. So then now we have a ratio. We get a ratio of rates, the rate at time t with respect to the rate initially is equal to the amount at time t over the amount initially. So notice here that this ratio of rates is equal to the ratio of the amounts. And so now look over here, we have the ratio here is equal to 1/2 raised to the power of the time elapsed divided by the half-life. So all we need to do at this point is substitute this in for this. So then our new equation is going to be the rate, right? Or, yeah, the rate at time t over the rate initially is then equal to 1/2 raised to the power of t over the half-life. So now we can use the rates we are given, and we can plug in everything else that we are given and solve for the missing part. So what is the missing part? So they want us to get how old is the skull. That is the time that has elapsed since the human being died. So that's t. So we are given the half-life. The half-life, of course, of carbon-14, that should be given. That's going to be, so T 1/2, that's going to be 5,715 years. So we can write that here. So T 1/2 is equal to 5,715 years. And we're given the rate at time t, right? So that's the decay rate here. And we're given the time 0. So we can write the rate time t over the rate at time, or at 0 initially. So we can put that in there. So that's going to be the rate at time t is 4.50 disintegrations minute per gram. So I can write DIS for disintegrations per minute per gram over, and then the rate of disintegration, the decay rate right now for living organisms is 15.3 disintegrations per minute per gram. So we know that. We know the half-life. So the only thing we don't know is the age. So that's T. That's the age of the skull. So now all we do is we plug everything in and solve. So here, so we got the rate nt, or here's our equation, right? So we're going to put rate in. So that's going to be 4.50 disintegrations per minute per gram over 15.3 disintegrations per minute per gram. And then that's going to be equal to 1/2 raised to the power of t over the half-life. But we know the half-life is 5,715 years. So let's put that in. That's going to be 5,715 years. So now we just go ahead and solve. Let's go ahead and divide this and find out what it is. So we got 4.5 divided by 15.3 equals, and we get 0.29411. The disintegrations per minute per gram cancel out. So we're going to get that equal to 1/2. Now we can take the log of this, but we'll just do this step first. So we have t over 5,715 years. Now we take the log of both sides. So we'll take the log of 0.29411 is equal to the log of 1/2 raised to that power, which is t over 5,715. Now, because of the laws of logs, we can take this power and put it in front. So then we're going to get, I'm going to write it over here for more room. Or do I have room here? Yeah, I have some room here. So here, I'm going to have the log of 0.29411 is equal to, I'm going to bring this to the front. So that's going to be T over 5,715. And that's going to be multiplied by the log of 1/2. Okay, so now what I can do is I can divide both sides by the log of 1/2 and get this by itself. So let's write that over here. So I'm going to divide both sides by log of 1/2, and I'm going to end up with the log of this number here, 0.29411 divided by the log of 1/2, and then that's going to be equal to this here. So T over 5,715 years. So I can go ahead and do this calculation. So I'm going to take the log of that and divide it by the log of 1/2. And I get 1.7655. So I get 1.7655 is equal to T over 5,715 years. Now all I do is multiply both sides by 5,715 years, right? So then this gets multiplied 5,715 years. That's going to be multiplied over here. So 5,715 years over there. So this cancels out. Now T, the age, is now equal to this number times this number. And when I do that calculation, let's do that. So multiply that by 5,715. I get 10,090 years. So T, so I'll write it down here. So T is equal to 10,090 years. So that, ladies and gentlemen, is the age of the skull. And so I hope this is helpful. That's how you go about solving this type of problem if you have rates. So remember, if you have rates instead of substances, you can substitute the rates in for the substances to use this equation here. So, and also this shows you that you could I could have actually used this equation too, because I could substitute the rates in for here as well. So either one of these equations would have worked. If you use this one, you would have to do an extra step to get to this form here. You'd have to do that anyway. So, so this one would cut your math a little bit shorter. I hope this is helpful. If you learned from this video, if this was interesting, entertaining in any way, let me know. Please like, share the video, hit that like button. Also, subscribe to my channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.